Good morning, good afternoon, and good evening, all of you. I'm Vipin Menon. I'm the developer at IBM, and I work for Instana, which is basically a monitoring tool for IBM Cloud. So let's get into the title without wasting any more time. So today we are going to discuss about distributed tracing. So let's get into the topics like what is distributed tracing, what is a tracer, then how we can visualize a trace, how the correlation happens. So this is what we are going to discuss today. Let's see the topics for today. So I will be taking you through a brief history of APM monitoring because I just wanted to make sure people who are in the room is very much comfortable with the topics which I'm discussing. So I will just give you a brief intro on what we are going to talk about so that whoever is in the room will have a complete understanding on the discussion. So I'll be also taking you through, as I mentioned, distributed tracing, then tracer. What's a tracer? What is the basic of a tracer? What are different types of spans? Then how the instrumentation happens? What is the payload? How the payload looks like? Then once you get the payload, how the correlation happens over the payload or over the transaction. Then I will be also giving you a small demo on the application, the sample application what I have, and I will show you how the traces look like on the monitoring tool. Then we will have some questions and answers. So let's get into the first slide. So let's talk about the very basic term here, like what is observability. So this is nothing but it's not a new term. This has been there in the market for some time. This is something which we say it's ability to understand the system. Like we have a system and we have to monitor any system. So we have to get some data from the system. So we collect the data and we try to analyze it and try to understand what is the state of the system. So system can be anything here. So that's what the base term about observability is. Now, how this has been there since history. So what is changed? So let's talk about what was there before. Then we'll see like what is the current system about. So this is how a basic system looked like before. I mean, before the cloud came into existence. So here, like you have a monolithic architecture where you have your business logic, the UI, the database, everything sitting together on a single system deployed on a web server, and they are all talking each other within the system itself, so that the monitoring was kind of very easy because everything was happening on a single stack. So if any issue happens on the system, we can basically look into the stack trace and try to understand what is really happening or what was really happening in that system. So this is history now. Now let's go to what is right now, what we have. Oh, sorry for that. Yeah, so this is how the modern workload look like. Now the monolithic architecture has been completely restructured. Now what we have is a microservice architecture, which works basically on SOA. So SOA is nothing but service-oriented architecture. So every service, so the entire system is now being split into different services. And these services will be deployed on different servers, different locations. They talk to each other from different locations, and you don't have direct control on any of these services. So the problem here is like this has been very easy now because the tight coupling has been now gone. So all the services has been now decoupled into different services. So what the main advantage over here is like the maintenance of the entire system has been very easy now. Like you can change any service at any point of time without breaking the entire system. The only thing is you have to make the SLA with the other services to be proper. Otherwise, you are free to make any changes, and the maintenance has been very easy now. But what has become complex now? The main part is the observability. So, how to observe this kind of system, which is spread across different system or different geographies? Like, how do you bring them together, and how to collect data, how to make them, how to make the correlation out of this data, and how do you see, like, how can you analyze the data and try to understand what is happening collectively inside the entire system? So this is a challenging part now because there is no single call stack. There is no correlation possible because the calls are made to an external system. So all the calls, all the stacks will be confined to that particular system, because of which the correlation wouldn't be possible. So that is a challenge we have with the current APM techniques. So that's where this distributed tracing comes into picture, where we have the flow of transaction. So the entire transaction over a distributed system, as I said previously, like the collectively all the services together, we collectively call them a distributed system, and we trace the data. Like when the transaction starts, when an HTTP request hits the initial service, it again calls multiple services to which all this spans spread across. Then it finally makes the HTTP response out of it. So from the request, from the initial HTTP request till the HTTP response, how many services it calls, like we need to have an understanding of what all calls it makes. So this is what is called a tracing. So we have to go through all the calls to understand when an HTTP request was made, what all things it has called, or what all functions it has called before it could figure out the HTTP response. So that is what a distributed tracing is. And the entire flow is called a transaction. So now let's understand what's a tracer. So now we have a distributed system, and every request being coming into the system is a transaction. And when a transaction starts and ends, you need to get the complete flow of it. And how do you get the complete flow of it? That happens with the help of a tracer. So tracer is nothing. It's a piece of code which sits inside the process. So you have a application process running in your system. And this process, we need to get data from this process to understand what all calls this makes. So for that, we are putting a tracer into the process itself, and it tries to collect the data what is required to us, and we make the correlation out of it. So if you see here, this is a monitored process. I mean by monitored process is like whatever process we want to monitor, it is actually residing in the system here. And on the left side, you see the request it makes, and on the right side, you see the request it serves, and on the right side, you see the request it makes. So it can be any process. So it can be a web server which can accept an HTTP request and give an HTTP response for you, and it can be a web client which makes another HTTP request. It can be a web server as well as a web client as well. So it will be making an HTTP request to an external server. So that's what you see on the right side. And it can be a messaging application where it can accept, where it will be reading data from the queues, or it can be a system where it makes use of RPC, or it on the right side, as you see, the system got these many requests. So it can make either HTTP request, or it can make a DB call to the underlying database to get the data what is required for the response, or it can be to any other functionalities. So that is what you're seeing on the right side. So this is a tracer. So tracer is sitting inside the process itself, and it is trying to understand what all the requests it got, and what is the request it makes, and what is the response it has, and try to correlate everything together. So now let's see the basics of the tracer. So as I mentioned, it can capture almost anything, the incoming calls, outgoing calls. Then it basically collects this information and it sends to the underlying agent. Agent is nothing but it is a monitoring tool. So the agent will be running on the system, and the tracer, which is now part of the monitoring process, will collect data from this process, and it will start sending to the agent, and agent will send it to the backend server, process it, and show it in a readable format so that we can understand like how the transaction has started and how it ended and what is the path it has taken. So these are the terminologies we should be familiar with when we talk about traces. So now you know what is a transaction. It is a complete response for an HTTP request. Then trace is the data what the tracer produces. So, and span, span is the building block of a trace. So we will talk about spans more when we get into the other slides. So let's understand span is the smallest building block of a trace data. So you have the complete trace data, and the trace data is built of spans. So now let's also understand the different types of span. So which is a root span. So root span is the first span which you don't see any parent for it. So we can assume this is the first span, or this is the initial span, or where the transaction starts. Everything starts from the root span. Now you have an entry span. So entry span is nothing but when it receives an incoming request into the service. So you have a service, and when it receives a request, then there is an entry span being constructed there. Then you have an exit span. So exit span is nothing. As I said, you might be remembering on the right side, we have seen like it was making an external DB call, or it was making, the process was making another HTTP request to the outside service. So at that time, it will mark an exit span. So when it hits the service, you get an entry. And when it goes out of the service, you get an exit. An intermediate span is something which lies within the service itself. Like it is not making any external call, but it is lying within the service itself. Like if it calls a function, and if that function is traced, then that is an intermediate span because it is not going out of the service. It is within the service itself. So these are the terminologies which we have to be very familiar with before we move further. So now let's understand, like as we were saying, we have the tracers, tracer get attached, or tracer lives in the process, and it collects the data and it sends the backend. So how this is really possible? So like what is a tracer basically? So as I said, it's a piece of code, but what is that piece of code? So that piece of code is an instrumented code. So basically what it does is like the tracer actually instruments the libraries or the frameworks which are involved in the language, and then it attaches to the process, and then it, whenever these functions which are instrumented gets an invoke, it actually collects the attributes or collects the data from that function. So it's basically an instrumented module which gets attached to the process, and it is like we just instrument the code to get the tracing data from it. So there are different types of instrumentation we do. So it is completely dependent on the language what we are trying to instrument. So there are different ways of doing it. For Java, basically we do bytecode instrumentation. So bytecode instrumentation, as you all know, I mean, we inject bytecode into the compiled bytecode, and then it actually creates an agent. It attaches to the Java JVM. So whatever instrumentation we are doing is it's an agent itself, and the agent gets attached to the Java process, and then the bytecode, whatever information is injected, and we collect data out of it. This is what we do for Java. And for Node.js and Python, you do monkey patching. This is again similar to bytecode instrumentation, but what we do is like we look into the well-known APIs of the frameworks which you are instrumenting, and what all functions is exported, or what function is exported, we just override them or we just replace them with the function what we are trying to instrument. So we just add our instrumented code and we just replace the function which we are trying to instrument. So that is what is monkey patching. Then there are languages where we won't be able to do any sort of instrumentation because they compile directly and they get into the machine language. So we won't be able to do any sort of instrumentation there. In those cases, we will have to have some modifications to the application itself and have some wrapper codes. So the provider or the vendor who is supporting with Tracer will give you the specific wrapper API, and the customer or whoever is using it will be modifying the application code is little bit to have these wrapper calls being made instead of making the actual service call. So this is the different types. So now let's get into the action. Let's try to understand how it works here. So this is a very simple application. So as you see, this is an SOA. So you have a Node.js service which is running on a different system. Then you have a Java application which is running on another system. They talk to each other because these are all microservices. And there are some database connectivities involved here. So Redis is basically here being used as a cache, and DB2 on the backend to get the actual data. So let's understand the flow of the application first. So first, the browser makes an HTTP request. It hits the Node.js application. Then Node.js actually makes a Redis access to get the cache information to load the initial data to the browser. At the same time, it then makes another HTTP request, which actually gives the actual content. So if you are looking for a list of shopping items, or so if that is a request you have made in the form of HTTP request, then basically it tries to get all the list of shopping items from the DB2 from the underlying database. Then that get shopping list is another service, this is Java service and is residing on a different system. So from the Node.js, it makes this Java service call. Then the Java actually picks the data from the DB and it makes a response to the Node.js application and serves it to the browser in the form of HTTP response. So this is the complete flow, and this complete flow is known as one transaction. Now let's see how the tracer adds span into it. Yeah, so now you see the first request hits the Node.js app. It made an entry span. So this is an entry span here. And you might be also seeing some attributes where T is equal to 1, which is the trace ID. So trace ID is something which is going to be the same across a transaction. So for the entire transaction, the trace ID is going to be the same. So that's how we bring out all the spans together and create a trace. And the next parameter is span. So span is again a random number or random generator. It generates a random 16-digit code, which is known as a span ID, which is unique to that span. So it created a span. Then P is the parent ID. So as you know, this is the first span. So, and there is no parent on the left side. So it is null over there. So now it has made a Redis call. So as soon as it hits the Redis call, it's an exit span now because it is going outside to the Redis and it exits. And as you see, the span data is already recorded now. Again, as you see, the transaction is the same. Then S, it created a new span, which is 2 here, for example. Then P is 1, so which is a parent ID. So it has come from the previous HTTP entry span, whose span ID is 1. So here the parent ID is going to be the span ID of the caller. So now you see it makes another HTTP request to get the shopping list. So which is again an exit span. So but it is an HTTP request. So it is actually again sending the same set of data, which is t is equal to 1 and s equal to 3 and p is equal to 1. So here p is 1. So p again parent is 1 because it has created from the HTTP entry span, and span s equal to 3. Then again the transaction code is the same. So that's what the entry it keeps whenever an entry or exit span happens. Now you see, now it has reached the Java service. So here again it has marked the entry of an HTTP entry span, and again the trace ID and the span ID and parent ID is collected, and now it makes another DB2 exit span. So it's a DB2 call now. So DB2, so it has to get the shopping data from the underlying DB2. So it makes an exit span. Now it returns the data back. Now it comes back to the exit span here, and now it reaches the entry span. So by this time, it has come all the way back to the caller, and now it actually knows like the timestamp, and now it have the duration of how much time it took for the response to come. So based on that, we create the span entries. So we will get into that in the next slide. Yeah, so this is how the span looks like. So it's basically JSON payload I have shown here. So it has some basic parameters which we just discussed. The first one being the trace ID, then the span ID, parent ID, and n is the name of the span. So basically this name is actually given by the instrumented code. So for every span it generates, it puts a name so that you can uniquely identify the service. So here it was a servlet service. So the name servlet. Then TS is a timestamp at which at when this was created, this span was created, and D is the duration, like how long it took for the span to complete, and K is the kind, or it's a flag which basically decides on some additional attributes like how much level of tracing has to be done, or whether the tracing has to be done or not. So which is not very important because it's an optional parameter. If you don't give it, like it will be always 1. And you have some attributes now, which is basically the data which it requires. So this is the instrumentation done by the tracer within your code to get the data. So basically it has understood, like it has made an HTTP request and the URL it calls, and the method, whether it was a get or post or put, then the host to which the call was made, and what is the status of this HTTP call. So this is how it looks like. Now let's get back to this slide again. If you see here, we have a problem, like the Node.js app is sitting on is residing on a different system, and Java application is residing on a different system. Now how because they are not communicating each other, because the trace has already had an exit span there, and this data never reaches the Java app because the tracing is confined to that service itself. So how the Java application is going to know, like when the like what is the trace ID that I have to put, or what is uh, the parent ID of mine. Span ID doesn't matter, but trace ID and parent ID really matters, because if this is not clear or proper, we won't be able to make any correlation out of it. So let's assume if you don't have this correlation from the Node.js app, so what will happen? If you don't have a correlation from Node.js app, then the Java application will think there is no, it's a fresh call, or it has to make a root span. So what happens is, like, it will create a trace ID by itself, and it will have a parent ID as set to null. So this is a problem. if this is set to null, then there won't be any correlation and you won't be able to associate these spans together and bring a transaction out of it. So that is what has happened on the left side. If you see the browser, so on the browser side, we don't have a control. So browser is sending the request, but it is not sending anything else. It is just sending a URL to access. And when it hits the front end app, it realized that, okay, I have to make a new span, the parent span, or a root span I have to make. So it just goes and creates a root span with parent ID set to null. But when it came to the Java app, it could understand that, okay, I'm not supposed to make a root span. I have to have some correlation because the caller has given me some information, so I have to make out of it. So this is where the correlation happens. So this is the correlation ID, which is called trace parent. This is as per the W3 spec. From Instana, we use different format of headers, but we do support the W3 standards as well. But in this case, like trace parent, as you see, it is actually modifying the HTTP metadata. The metadata of HTTP header is modified, and it adds this information into the HTTP header. So basically, it is adding the trace ID, and it is also adding the span ID. And the last one is the optional parameter, which is anyways not very important. So we will talk about the first two. So 193 is sent from the Node.js application by modifying the metadata of the HTTP header, and it is sent to the Java application. And that's how the Java application realizes that I have to create an entry span with trace ID and parent ID set from the caller. So this is a trace correlation, what we are discussing about. And if you're making a call where there is no metadata, there is no metadata supported, then you won't be able to have this correlation. So for example, if you see the Redis or DB2, this correlation metadata can't be put in because the metadata, it doesn't support for the metadata information to be passed. For example, SAP has RFC. It makes a remote function call. So this RFC doesn't support any metadata to be added to its headers. So that's where when it exits, you won't be able to trace it further. So you will have a full stop, and you will have to wait for the response to come from the underlying system, which doesn't support this correlation. Then it gets back, and you have to make a correlation out of it. So if you look at this scenario, where I have marked no correlation headers, we really don't need of that correlation, if you see, because in Redis and DB2, when an external DB2 call or when an external SQL call is made to any of these DBs, you actually have a exit span, and you have a timestamp, and you can wait for the response to come. And when the response comes, you will have the duration of how long it took for the response to come. You can add with the timestamp, and you can understand how much of time it took for the DB2 or for the Redis to respond to the request we made. So the only thing is there won't be any exclusive tracing possible on these DBs, which anyways the customer or the user won't be okay with, because the basic tracing what we do is SQL tracing. So they won't be able to they won't be happy to do that. So, but anyways, for an overall understanding of the transaction, we are good with the current timestamps and the duration, and we can easily make out a meaningful information out of it. And if you see the browser side, again, there is something called website monitoring. So we can have your website added For example, on Instana, we have website monitoring. So you can add your web server uh, into the Instana, and Instana will be able to monitor the website itself and try to understand from what all IPs the requests are coming, then from what geographies these requests come, what is IP address, and what is the overall number of accounts. So all these basic information you get when you do website monitoring, and this information can be clubbed with the underlying span data which is already there with the tracer, and you can bring them together and you can make a meaningful information out of it. So this is how the correlation works on trace. So now we can go for a small demo. So please feel free to post your questions. I will take them at the end. Right now, I don't see any. So I will go ahead with the demo. Okay, let me take the Instana screen. I hope my screen is visible here. So this is my the system. I mean, this is my laptop itself. So the overall usage, memory, load, everything is being shown here is from the Instana dashboard. So I'm using Instana for showcasing this use case of tracing here. So if you see here, we have my Mac and some basic information about the system itself. And on this system, I have these many applications running. And the use case for tracers, I have created a Spring Boot application where I have exposed two services. So Spring Service A and Service B, both are running let's assume they are running on different systems, but I have deployed on my laptop itself. So that is why it is being shown under my system. Like you have two services running from Spring Boot. And if you see, if you click on Service A, it takes you to the basic service dashboard. So it will give you the basic information about the sessions, requests, and it will also tell you the service which is exposed in this application. So let's go to the service itself. So this is the dashboard. So on this dashboard, I will show you the endpoints. Flow here. Yeah, this is the Spring Service A. This is what we are looking at now. So right now it is shown as an individual service. Now let's have some hits on it. So I'm just going to make few hits on this service. Now, if you see the summary page, yeah, you will start seeing the data which is coming here. Yes, the calls per second. So the total calls, yeah, I made 4 hits. Okay, sorry. Yeah, I made 4 hits now. And this is the average time it took. So no erroneous calls. This is the latency. And now let's go to the flow. So now you see as I hit on the service A, it actually made a call to service B. So it made an exit span and it called service B. And this is a flow it generated. And now let's go to the endpoints. Okay, let's go from here. 1 second. System is a bit slow. Yeah, so this is a service screen. Now I will go to analyze calls. So you can analyze your call here. I will make this time last 5 minutes so that you can see the call here. Yeah, so this is the call I hit. Now it has recorded the calls here. Now you just click on it and you will see the spans. So as you see here, this is the URL I hit, and it made another call from this service to this service, and it took 416 milliseconds. And this is the service I hit, and overall it took 663 milliseconds, out of which this 416 was taken by this service, which is the another service which this service called. Now, at the same time, you can also see the data. Second, I'll just move this. Okay. Yeah. So here you will see the source is not monitored because source is web browser. So it is not monitored here because I have not set any website monitoring. So it will always show as not monitored. And this is what you see when you hit your DB service or DB2. If it is not monitored, then it will show your destination as not monitored. So here the request has come from web browser. So it is saying it is not monitored by Instana. Now the destination is Spring to Kong. So this is service I hit. Now it has actually created this span. So this is a span which it got from this response. Now let's go to the service. This is second service. This is the internal service which was called by the actual service. Now if you see this, now it tells you the source because the source is now monitored by Instana. So it will tell you it has come from here, and it will also give you the stack trace stack trace which was responsible to make this second call, Spring Welcome. Then it has actually recorded few other attributes along with the span information. So it has the request path, then the status code, then this is a destination call here. So on the destination, it says it is the inner service, Spring Welcome. Then it actually has called this Spring Service B. Then this is a destination, and again, it has created a span out of it. And this is your full transaction here because the request was made to here. It made another request to this service. Then it got responded to this back. Then from here, it went back to the browser. So if you look, the overall transaction took 663 milliseconds, and out of which you got this 416, and the span is recorded here, and the other details. So and this is how the usual monitoring of traces looks like. In this case, it is Instana. So yeah, so this is the analytics page, and yeah, you can go back to your service again from here, and you see your infrastructure, and you can go back to your infrastructure back. Yeah. So this is a typical flow of the complete complete tracing done using a tracer. So here you have the Node.js tracer. So I will pause here. I think I have completed the demo, and just a moment. I hope I'm still sharing my screen. Okay, somehow it stopped. Yeah, so here I have some references section. So please feel free to go through these. So I have added some additional pages which would be helpful to you. For example, this one, like how the instrumentation is done on a Java application. This is a blog created by one of our developer. Then you have the tracing specification. So you can go through that also. And the basic observability stuffs which we discussed, and how the monitoring of traces, all these things I have covered here. and this is the W3 standard. So please refer these links for more information. Thank you. I will see to the chats for any topics. Sorry, any questions? Okay, I see one question. Can a span be modified to contain information about the timings of the internal code? You have different functions and want to check which function is taking how long. Yeah, so the usual span won't have much of information because it will have only the basic attributes. For this, we have something called Instana SDK, which is an exclusive tracer. So this tracer we have to add as a dependency into your application. And in the application code, you have to make some modifications, like you have to add these tags like span entry, span exit. So you will have to manually do that into the function which you want to monitor. And this span interface takes up few attributes, and you can customize it. You can have custom information in it, and you can basically add whatever data you want as a part of your span, and you can run it with, you can just have your tracer run with your application. So it will become your part of your application, and you run it and you will start seeing this data. But it won't work out of the box because it is a customized content that you want to see. So that sort of modification you will have to do. So we have SDKs for most of the frameworks. So you can start and try to see if, you can use those SDKs for doing this kind of activity.